Welcome back, everybody. So we've got the key up here for sections 6, 7 homework. So go ahead and start checking your answers. Let me write the new homework here up on the board too. Do that. I'm going to pull it together. Tuesday morning. Liam, relax.
No, you're relaxing.
That's right. Charlie, it's a joke. It's a joke. Word 63. Okay, so there's 15, 16, 17, 18, 19, 20, 21, 22. Make sure this is the part that I really need on there. I need the end behavior. Okay? I need the end behavior. And I need it written like that. And I'm going to be pretty picky about the notation. Okay, I know it seems like it's a lot. It seems like it's complicated. But remember that in the notation, like, take a look at this. Do we see how every time I've got the exact same thing, oops, I went too far there. I've got the exact same thing written, with the exception I'm changing the function name, right? As x goes to the left, y does this. As x goes to the right, y does this. As x goes to the left, y does this. As x goes to the right, y does this. Left, right, left, right. Okay? So that's the notation that I need to see. Yes?
Will you not point if you don't put the and?
No. So here, let me fix it. Is that better? There we go. That's what I need to see. Does that make sense? Is that better?
Yep.
Okay, got it. Questions about anything 15 to 22? Okay. Here is number 24. I've got f of x is equal to 25x squared minus 4. So the first thing I would do is figure out what the end behavior is. Well, since this is a positive even, I would say, okay, positive even right away, right up top here, positive even, both going up and to the pen here, both going up on the left and right side. Okay? This is me. This is my arms. Okay. Got really long arms. Now, I know it's going up and to the left and to the right, and now all I have to do is figure out where my zeros are, my critical points. Well, I take my zeros of f of x, and I find it to be, I can factor that, 5x plus 2, 5x minus 2. Honestly, you can just straight up solve it, because there's no b term. Add the 4, divide by 25, and take the square root. Turns out to be negative 2 pips, positive 2 pips, or negative 0.4, positive 0.4. Now, at that point, I would then want to make myself a little table because I want to know what's going on in between there. It would be a good idea because this is so, we would only see one other point there. Like if I were to truly want to make my table, as I told you yesterday, you really want to figure out what's going on in between the zeros. Well, since I know that it's going up on the right and up on the left, well, that would mean I would only really need one point in that table, 0, comma, negative 4. I plug in 0, I get negative 4. But it might be a good idea to make a couple more points just to see what's happening on the left and right side. How steep does it go up on the left and right side? So that's why you see here is f of negative 1, and then f of 0, f of 1. Questions about that? That was kind of an easier one. This is the doozy. This is the fun one. I want to walk through this one kind of slowly, just so you know exactly what's happening. Because I'll tell you what, this is going to be more likely the ones that are going to be on your individual and group test. Yes, there's one on a group and then one on your individual. I was kind of nice to you on your individual test, though. It's one that doesn't have any, I shouldn't say any, doesn't have many P's or Q's. Okay, so here's what I mean when I say about the difficulty. Taking a look at this function, I can't factor it, right? I can't factor it. So I would then take my values of P and divide them by my values of Q. When I say values, I mean factors. Okay, so the factors of P, I've got 48. So plus or minus 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. How do I get those numbers? Well, I just quite simply just figure out what are my factor pairs, right? 1 times 48, 2 times 24, 3 times 16, 4 times 12, and 6 times 8. Okay? And then this problem is, I don't want to say easier in the fact, but it's not as bad as it could be because my leading coefficient is 1. When my leading coefficient is 1, I can say that my P over Q list is really just my P list, right? Because I just divide everything by 1, which is essentially the same thing. So that's why you see all of those possible rational roots. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I got 20 possibilities. Looks like we tried to do -2 first here. Did not work out because I did not get a 0 here. Then it looks like I was pretty lucky here. Got a -1. I plugged it in. I got x to the third minus 28x plus 48. Now, you may have been stuck at that point thinking, well, what do I do now? Because that doesn't factor, and it's not quadratic. Be careful. It's not quadratic. It's cubic. I can't use the quadratic formula. So what do I do next? Keep going in your P over Q list. You got to go back and say, okay, these are still the possible rational roots. Is there anything else in there that I could possibly do? Well, it turns out a +2 works as well. Okay, so, and then we factor it down. It looks like there were 4 possibilities. So your work might have looked a little different because there were 4 different possibilities of possible rational roots. It looks like -1, +2, -6, and +4. Those are the 4 possible rational roots that you could have gotten using synthetic division out of that list. So really, we had a 4 in 20 shot of getting it on the first try. So, not too bad. 1 in 5, 20%. All right, so my zeros are -1, +2, -6, and +4 once we get it all factored down. Now, at that point, I plot those. -1, +2, -6, +4. I should have discussed the end behavior right at the beginning and seen that, okay, this is a positive even. So again, positive even right up at the start. That goes up on the left and up on the right. So I know that on either side of my far right and far left zeros, it does go up and up. And then we make a table. I want to pick something in between -6 and -1. Looks like we picked a -3. I want to pick something in between -1 and +2. Looks like we picked a 0. Something in between 2 and 4. We picked a 3. Now, these points here and here, I don't need those. I used to make my students do that. But if we truly know the end behavior, do we really need to do that on the far left and far right side? No, as long as you can understand what the end behavior is doing. If you have trouble figuring out end behavior, plot points on either side. That's a very easy way to figure out what's going on the far left and far right side without needing to understand end behavior. So we see these 3 points here. These are the ones you definitely need to do. And again, you could have picked any points in between there. I just picked some easy points in between there. -3, 0, and +3. Okay, -3 being something in between here and here. I could have picked -2, -3, -4, -5, whatever. In between -1 and 2, I could have picked 0 or 1. In between 2 and 3, pick 3. Or sorry, 2 and 4, pick 3. And then we have these coordinates here. Now, that's pretty big. So you got to kind of scale it as needed. But it looks like -210, +48, negative 36, which makes sense because, you know, if you're thinking about a degree of 4, that was the one that goes up on either side, and I should see 3 turning points. It should decrease, increase, decrease, increase, right? So 1, 2, 3 turning points. 3 what we would call local maximums or minimum points. Looks like I have 2 local minimums and 1 local maximum. Okay. Questions on that? Because that's about the difficulty that I could see on definitely like the group. I mean, I might give you something wacky like that on the group, like something with a 48 on there. Because then you could say like, okay, you try this, you try this, you try this. Let's figure out which one is going to be a solution. You know. Okay. Now let me talk about finding the local maximums and local minimums. This was the thing that I did a video on. So if you watched the video, great. You can kind of tune me out at this point. If you didn't watch the video, it's really quite easy. You just have to know what to do in your calculators. So that's all I'm going to do. Let me get out my calculator. And actually, I'm going to pull up the book page. Let me get the exact problem numbers. What page was this on? Can somebody help me out?
458.
458. I know it's in chapter 6, 458. Okay, page 458. Looks like I want to do which numbers? I want to do 28 and 30. 28 and 30. Okay, let me just snap those over. Oh, I kind of chopped off its head, but that's okay. Perfect. All right. Didn't fit. Right there. All right, here we go. So taking a look at 28, I'll do both of these. I want to figure out where my local maximums and minimums are, and to do so, I am first going to plot these in my calculator. I'm going to go to y equals, and I'm just going to plug that in. X to the third minus 4x squared plus x plus 1. X to the third minus 4x squared plus x plus 1. I'm going to hit zoom 6 because I know I made my graph all wacky when I was making the video. Do I see the minimums and maximum points on my screen? Yes. If I didn't see it on my screen, like the one that I did in the video, if I didn't see my screen, I would need to manipulate my window so that I saw the minimums and maximum points. So basically here for 28, I see one maximum point right here, and I see one minimum point right there. Let's figure out exactly where they are. To do so, well, if that's a maximum point, I would just calculate maximum. Quite simply that. It's choice 4. Now it's going to ask me 3 questions, a left bound, a right bound, and a guess. For the left bound, I'm going to trace somewhere to the left of the peak. Hit enter. For the right bound, I'm just going to trace somewhere to the right of the peak. Hit enter. And then it's going to ask me to guess somewhere in the middle because all the calculator is doing is running values in the middle to see which one's high. And it looks like they got, this is my actual maximum point. Now, people would say that the maximum value is the y value of the function, and it occurs at 0.13. Yeah. Honestly, like the book actually gives just a 1.06. Right? That's just the maximum value. Okay? So really, just the y value is acceptable, but I like to say the y value at the certain x value, like the local maximum is 1.06 at 0.13. Okay, let's do that local minimum right there. You do the exact same process. So I can calculate minimum value, which is 3. And now I just go somewhere to the left of the valley, hit enter, trace over somewhere to the right of it, hit enter, and then I guess somewhere in the middle. And there's my local minimum point, negative 5.88. Okay. And it occurs at 2.53. You don't understand how to do that right now, like algebraically. You actually learn how to do that in calculus. You actually learn how to figure out what those values are algebraically. Basically, you find the derivative and set the derivative equal to 0. But there's number 30 as well. That one does not have a local minimum point. It's just a local maximum point. It's pretty simple when you just see the calculator do it. You know, it's not very difficult once you know the keystrokes. All right, any questions on the homework? Anything else we wanted to talk through? I feel like we went over it pretty thoroughly. All right, so section 6.8 that we're going to be looking at today. Again, in these three sections of, they don't really fit in anywhere else. Today what we're going to be looking at are transformations. Now, we've done transformations of equations before. Transformations of linear, transformations of quadratic. What we're going to be looking at now is transformations of polynomials. Extending our knowledge of transformations onto polynomials. All right. Now, just like you could perform transformations on polynomial functions that we've done before, like quadratics and linears, we can do the same thing on polynomials. Okay. These are the rules. You see them right in front of you. These are the rules for transformation. Okay. I'll tell you this right now. These are not new. Okay. Everything in this middle column is not new. That should, I mean, we may have to dust off the cobwebs a little bit, but that is not new. That should be in your brain somewhere, locked away. Okay, that should be in your brain somewhere. What's new is how we apply it. What's new is how we apply it to polynomials. Okay? For example, vertical translations. Remember, vertical translation is that shift up or down. I'm adding or subtracting something to the end of the function. Horizontal translation, I'm replacing, remember, anything horizontal, I'm replacing the x value with, and in this case, translation, x minus h. So if it was like a right 2, I'd move it x minus 2 inside the parentheses. I'd replace every x value with x minus 2. If it was a left 1, you'd go x plus, or remember, horizontal are the opposites. Right, those are the weird ones. Vertical stretch of compression, I'm just multiplying a times f of x, straight up a, like if it's vertical stretch by 6, it's just 6 times the entire function. If it's a vertical compression by 1/3, it's 1/3 times the entire function. Horizontal stretch of compression, that's when I take 1 over b and multiply it to x and put it in for x. Okay? Every time where I see x, I plug it in and 1 over b. And the reflections there, I'll take a negative on the outside, it reflects across the x-axis. If I put a negative on the inside, it reflects across the y-axis. So I gave you an example down there, and it's actually a quadratic example, something that we've kind of already done before, but aren't quadratic polynomials anyway. So let's investigate it using this function. We've got f of x is equal to 2x squared plus 3x minus 1. Let's perform these transformations on that function. Okay. Let's first start off. Let's just go down the list. Let's say an up 2. An up 2. Well, that would just take f of x and map it to f of x plus 2, right? On the outside. So that would be, g of x would be 2x squared plus 3x, and then minus 1 plus 2. You see that plus 2 sitting out there on the end? Just going up 2 units. So g of x would be 2x squared plus 3x, and instead of a minus 1, it'll turn into a plus 1. Sorry, I kind of ran through my x squared there. If I were to go down, let's go down 3. I don't know, just making these up. That would be f of x is going to map to 3. F of x is going to map to f of x minus 3. So that would just take 2x squared plus 3x minus 1 minus 3. See that? Look at that minus 3 sitting out there on the end. And then to simplify the whole thing, you would just take the constants together. Let's think about right. Okay? A right, how many? 2. What'd you say? 7. Right 7. So that's going to take f of x and map it to f of x minus 7, right? Okay, well that means that if it's f of x minus 7, I'm going to replace x. Everywhere where I saw x within the function, I'm going to replace it with an x minus 7. So g of x is going to be 2 times x minus 7 squared plus 3 times x minus 7 minus 1. You see what I did there? You don't just replace it once, you replace it every single time. Now here's what's funky about that. Could I leave my answer? I'm going to leave it here for right now because I'm going to be doing other examples a little bit later. But can I leave my answer like this? No. I've got to FOIL that out. I've got to distribute that 3. I've got to combine all my like terms in the end. Right? So it's going to be complicated when we have things that we plug in for x. And obviously, if I were to go to the left, that minus would just turn into a plus. Right? So let's say we want to go, so that's up and down, left and right. Let's do a vertical stretch by 5. Okay, that's going to take f of x and map it to 5 times f of x. Right? That's going to be 5 times f of x. Okay, so that would be, g of x would be 5 times the entirety, 2x squared plus 3x minus 1. And that one's pretty easy to reduce, so I'll just go ahead and do that. That would just be 10x squared plus 15x minus 5. All right. That would be a vertical stretch, multiplying the entire function by a certain amount. A vertical compression would just be a fraction multiplied by the entire thing, right? So if I wanted a vertical compression by 1/2, that's just taking f of x and mapping it to f of 1/2 x. So that would mean it would be g of x would be 1/2 times this entire 2x squared plus 3x minus 1. So just quite simply because it's easy to reduce, x squared plus 3/2 x minus 1/2. Just distributing it in. And then the last ones that we have to do, without talking about the reflections, the last ones that we have to do are the horizontal stretch and compression. Let's do horizontal stretch by 3. Horizontal stretch by 3. Now remember what that means. That means that it's going to be f of x is going to map to f of 1/3 x. Right? That's the weird one. Horizontal stuff is the weird one. So it's going to actually turn into a fraction at that point. It's going to be 1/3 x. So that means g of x, and since it's horizontal, it's going to go in place of x. Instead of 2x squared, it's going to be 2 times 1/3 x squared. Instead of plus 3x, it's going to be plus 3 times 1/3 x minus 1. Do you notice how I replace 1/3 x for x? You do that every time something is horizontal. So g of x would be 2 times, now don't forget to distribute this power, 2 times 1/9 x squared plus, oh, look at that, 3 times 1/3, I'm playing x, just 1. And then, so I believe, just reduce that down, 2/9 x squared plus x minus 1. Okay. Now the reflections, remember that the reflection across the x-axis, you take a y value, right? So the negative goes to the entire thing, just like a vertical stretch compression. The reflection across the y-axis, you plug negative in for each x, and then you kind of evaluate using the power. And we'll do some examples like that. Let's flip it over onto the back and actually try some out here. All right, for f of x is equal to x to the 3rd minus 6. We're going to write the rule for each function and sketch its graph. I would say for this, we could do our calculator to sketch the graph. Just kind of make sure that it's doing what we think it should. Be prepared to, I think there's maybe something on the group test, I think. I'm kind of remembering from last year. A couple where I do ask you to like just make a vague sketch of what's going on without your calculator. And not anything precise like we did on the homework from last night, but just a vague sketch, just so I can see all the transformations that are going on. So g of x is equal to f of x minus 2. First off, let's identify what is that transformation? What is that? What is an f of x minus 2? Down 2. So that means g of x is going to be, so we can say that's a down 2. G of x is going to be x to the third minus 6, and then a minus 2. Right? That's f of x, and then it's just a minus 2. So g of x is going to be x to the third minus 8. Oh, we could sketch that. Isn't that a cubic just shifted down a total of 8 units? Yeah. It's our parent function just going down 1, 2, 3, 4, 5, 6, 7, 8. And we can draw our parent cubic function. Something like that. Whenever it says sketch, it's a rough sketch. If you wanted to put it in your calculator, you could, just to verify what's going on. Put one in the y1, put one in the y2. Okay, so we're still working with the same function, x to the third minus 6. But now what we're going to do is we're going to do that. What is that transformation? What is that transformation? Left 3. Left 3. Be careful with that one. That is a left 3. Even though I see a plus 3, that's actually moving to the left 3 units. Okay, so the original function, x to the third minus 6. That's f. So now I'm going to take f of x plus 3. Okay, what does that mean? That means I'm going to put this in for x and compute it. So h of x is going to be equal to x plus, it was x to the third, so it's x plus 3 to the third minus 6. And now I hope we see the implications of what we have to do. We have to do this. Can we just distribute that third power? I'll do that. 8. We actually have to take this. Right? We can't just distribute that power. We've actually got to take that to the third power. I guess we could have used Pascal's triangle. That's a throwback. Multiply that together. H of x is equal to, we got x plus 3. And then foiling those together, that's x squared. 3x and 3x makes 6x. 3 times 3 is 9. And then we multiply in the x plus 3. So h of x is equal to x cubed, x squared, 9x, 3x squared, 18x, 27. And then don't forget about the minus 6. Guys, honestly, that's one of the pieces where people will forget. If you've got something and adding or subtracting on it out there on the end, there's a tendency to forget that. Don't do that. Please don't do that. All right, so my final h of x is x to the third plus 9x squared plus 27x plus 27 minus 6. Nope. Duh. You can actually take 27 minus 6 to make 21. Crazy, right? Who'd have thought? So, when you're doing something, I'll let you in on a little secret. Isn't it really a secret? When you're doing something horizontal, tendency is that's going to be a little bit more work than doing something vertical. Because doing something horizontal will change what's inside your x value, which will potentially mean that you have to take that exponent to everything inside that parenthesis. Okay, let's take a look here. Let f of x be x to the third plus 5x squared minus 8x plus 1. Write a function g that performs the transformation. So let's do some reflections. Let's reflect across the x-axis. And then the next one is reflect across the y-axis. So remember that the transformation is f of x is going to map to, okay, remember, reflecting across the x-axis changes the verticality of it, right? So it's going to be a negative f of x, negative y value, negative f of x. All right, so that my new g is going to be negative, and then my entire f of x. My entire x to the third plus 5x squared minus 8x plus 1. Okay, when you do something to the outside, this is just like a vertical stretch of compression. When you do something to the outside, you got to do it to the whole thing. So g of x is going to be negative x to the third minus 5x squared plus 8x minus 1. Let's do a reflection across the y-axis. Let me bring that one up here. Same function, but now we're going to reflect it across the y-axis, which means that it's going to change from negative f of x to f of negative x. So what does that change really? Well, now a negative goes in for every x value. So it was x to the third, so g of x is now going to be negative x to the third. And then it was plus 5x squared, so it's going to be plus 5 negative x squared. And then it was minus 8x, so it's minus 8 times negative x, and then plus 1. Again, I'm just putting in negative x in for every x value that was there. Okay, what does that mean? That means that I've got to take this negative x to the third. Well, what happens when I take a negative to the third power? It stays there. So g of x is equal to negative x to the third. What happens when I take a negative to the second? It goes away. So this one actually stayed plus 5x squared. Negative x times negative 8 is a positive 8, and then a plus 1. So, moral of the story here is that if I'm reflecting across the y-axis, it's only going to change some of the terms. It's only going to change the terms that have an odd degree. Okay? It's only going to change the terms that have an odd degree, because that's when, if I raise it to that power, the negative is going to stay. Okay. Let f of x be this function here. It says graph f and g on the same coordinate plane. If you want to graph to kind of double check to see is it doing what I think it should be doing, by all means, go for it. We're going to describe g as a transformation on f and then write the new function. All right, so what is the transformation? What transformation are we talking about here, where I take 1/2 of f of x? What type is that? It's something. Very good, Alex. Very good. By? Good. This is a vertical compression by 1/2. Vertical compression by 1/2. Okay, so that's describing g as a transformation of f. And now let's actually perform the transformation. All right, so that means g of x is going to be 1/2 of the entirety of f of x, 2x to the fourth minus 6x squared plus 1. So g of x is going to be x to the fourth minus 3x squared plus 1/2. Again, it would be a good idea if you plugged in that function into the calculator, x to the fourth minus 3x squared plus 1/2, and then plugged in our regular to make sure, okay, did it really vertically compress by a factor of 1/2? You know, visually see, did it actually do what you think it should have done? Let's take a look here at the next one. Okay, what is that? What is that? What is that? Yeah, horizontal stretch by 3. Good. Horizontal stretch by 3. Horizontal stretch by 3. Because again, the b value is at 1 over b, so 1 over 3. That's that 3, that b value. Horizontal stretch by 3. All right, so that means g of x is going to be, all right, now I've got to take that function and remove x, and in its place write 1/3 x. So it was 2x to the fourth, so it's going to be 2 times 1/3 x to the fourth. It was minus 6x squared, so it's going to be minus 6 times 1/3 x squared. And then we got this plus 1. Notice again, I'm taking out x, and in its place I'm writing 1/3 x. This is the case where I can distribute that power in, because this is not a, there's no plus or minus signs. It's not a binomial, it's still monomial. So I can just distribute that power in. So g of x is equal to 2 times, okay, 1/3 to the fourth. That's 1 to the fourth over 3 to the fourth. So 1 over 81 x to the fourth. And then this is minus 6 times 1/9 x squared plus 1. I'm just distributing that power in, taking 1/3 to the fourth x to the fourth, 1/3 squared x squared. And now, leaving it as fraction form, g of x is equal to, because that's easier, 2/81 x to the fourth minus, okay, 6/9 would be 2/3. 2/3 x squared plus 1. Again, when doing something horizontal, our life is a little bit more complicated. It just is the case, because I'm replacing things for the x value. Write a function that transforms that function in the following ways. So now what we're going to do is we're going to chain it together. We're going to do a couple transformations in one problem. Like for example here, I want to reflect this across the y-axis and then shift it 2 units down. Reflect it across the y-axis, shift it 2 units down. So let's take the first transformation. Reflecting across the y-axis, what rule is that? F of x maps to what? F of negative x. F of negative x. Oops. I want to write there. F of negative x. So that means my halfway there g of x is 6 times negative x to the third minus 3. You follow me there? All right, well, take negative x to the third power. The negative is going to stick. So g of x is going to be equal to negative 6x to the third minus 3. But I'm not done yet. I have to now take it 2 units down, which means f of x is now going to map to f of x minus 2. Okay, so g of x was then going to be negative 6x to the third minus 3 minus 2. All right, so g of x is negative 6x to the third minus 5, all said and done. And those are relatively easy transformations, right? Shifting down is really quite easy, just add and subtract in the end. Reflecting across the y-axis, just plugging in negative for the x values. The next one, not so much. I still am going to use this same function, x to the third, 6x to the third minus 3. F of x is 6x to the third minus 3. Okay, I'm going to compress it vertically and then shift it right 2 units. I'm going to compress it vertically and then shift it right 2 units. So let's do vertical compression first. So vertical compression is going to be, real, come on, stop it. So annoying. F of x is going to map to 1/3 f of x. Right? That's a vertical compression by 1/3. All right, so my halfway there g of x is going to be 1/3 times 6x cubed minus 3. All right, let's distribute in that 1/3. G is then going to be 2x to the third minus 1. Okay, well that wasn't so bad, right? Oof, 2 units right. A very small statement with big implications. 2 units right. F of x is going to map to f of, putting in parentheses is not fun, especially when it's adding or subtracting. Because now what does that mean? That means now g of x has to look like this. 2 times very common mistake and very crucial mistake, people leaving that on an answer blank. Yes, that's technically true, but is it simplified? No, you must simplify it. And if you leave that as an answer, you're going to be cutting off a lot of work. So let's just take this and take that x minus 2 to the third power. And then we'll bring everything else in. Oops, x minus 2. And then we'll bring everything else in. Let's multiply those two together. So I've got an x minus 2 times x squared minus 4x plus 4. That's just quick foiling. Square the first, double the product, square the last. And we'll bring in the x. X to the third minus 4x squared plus 4x. Minus 2x squared plus 8x minus 8. And we'll simplify it down to x to the third minus 6x squared plus 12x minus 8. So that's 2x minus 2 to the third power. So now this is 2 times that minus 1. Okay, so g of x is 2x cubed minus 12x squared plus 24x minus 16 minus 1. The tendency is that minus 1 kind of gets like lost along the way. Stay along for the ride, buddy. Because now we have to factor it in. We get a 2x to the third minus 12x squared plus 24x minus 17. And again, if you wanted to, you could always plug it into your calculator to make sure that it did those transformations. Yes? It was all the way at the very beginning of the problem.
So you just left it out.
Yeah, this work was all just to do that. That make sense? Yeah. All right, so long, everybody. Play along at home.